Today we're talking about the binomial theorem. The goal is to use the binomial theorem to expand binomials raised to whole numbered exponents. But before we do that, we're going to talk about something that doesn't seem to relate. It's Pascal's triangle. Anybody remember Pascal's triangle? You start with a, now it's not a geometric triangle. It's triangular. It's a triangular organization or set of numbers. We start on the outside of the triangle with some ones, like on the outside, in that sort of shape. And then to get the numbers on the inside, you remember what you do? You add the kind of numbers diagonally above to get the number down here. So 1 plus 1 is 2, so that should be a 2 right there. And that is really a recursive sequence line of thought right there, isn't it? So Pascal's triangle is generated recursively. Okay, so the next row, you're going to start out with a 1, make the 1 a little wider than that one, and then you're going to add, to get the next number, you're going to add the 1 and the 2 above it and put it right in between the 1 and the 2, but below it, right? Like so. And then go past the 2 horizontally and then add the 2 and the 1 and get another 3, and then put a 1 on the end, and you've got that row of the triangle. And then what would the next row be, number-wise?
1, 4, 6, 4, 1.
1, 4, 6, 4, 1. And let's do one more just for fun.
1, 5, 10, 10, 5, 1.
1, 5, 10, 10, 5, 1. Does everybody see how the triangle is generated? Okay, this first top row, which only contains the 1, is called row 0. So we start counting at 0 here. So we'll use n for that. N equals 0. This is row n equals 0. This is row n equals 1, the one with the 1 and the 1. Row n equals 2 is the one with the 1, 2, 1, and then so on and so forth. So the way to remember it is the one with the 3's in the middle, that's row 3. The one with the 4 right after the initial 1 is row 4. But it's really the 5th row, right? And then the one with the 5 right after the 1 is row 5, but it's really the 6th row. So that's kind of weird. You got to get used to that. Okay, Pascal's triangle. Okay, it turns out that the numbers in Pascal's triangle form the coefficients of a binomial when you multiply it out according to an exponent of n. So check it out. Here's a formula you may have memorized. If you take a plus b and square it out, so n is 2 in this case. What's the formula for that? A squared plus 2ab plus b squared. And look at the coefficients, 1, 2, 1, which exactly match the numbers in what we call row 2 of Pascal's triangle. And that's not a coincidence. If I took, and I'm not going to take the time to do it here, but if I took a plus b cubed, the coefficients that you'd get when you multiply that out would be exactly 1 of whatever the, whatever the a times whatever the power of a times whatever the power of b is. The coefficients would be 1, 3, 3, 1. And if I took a plus b to the 4th power and multiplied it out, the coefficients would be 1, 4, 6, 4, 1. If n is relatively low, then Pascal's triangle is a very quick way to multiply something out. Well, not just something, a binomial brought to a whole number power. So would you agree that a plus b cubed would be a plus b quantity, well, just a plus b times a plus b quantity squared? But we already know what a plus b quantity squared is. So a plus b cubed would be the quantity a plus b times a squared plus 2ab plus b squared. So we just need to multiply this out, combine like terms, and we'll have a plus b cubed. So just remember what you do when you multiply out polynomials, actually. Distribute this a right here to every term. It's really just distribution, right? So all the powers of a go up by 1. So a squared would go to a cubed, 2ab would go to a squared b, and b squared would get a factor of a b squared. And then distribute b so that in each term, each factor of b goes up, the exponent goes up by 1. What do you get? So b times a squared is the same as what? It's the same as a squared b, right? So I'm going to line it up with its like term, 1a squared b right there. So distribute a to b rather to a squared, I get a squared b if I turn the multiplication around. Distribute b to 2ab, what do you get?
2ab squared.
Plus 2ab squared. Distribute b to b squared and you get b cubed. Add up the like terms, I'm adding vertically here. You know, with a cubed plus 3a squared b plus 3ab squared plus b cubed. And look at the coefficients, you guys. There's 1, 3, 3, and 1, which exactly match Pascal's triangle in row number 3, the n here corresponding with the exponent here. Okay? Doesn't prove that it works for Pascal's triangle, but it makes you believe it a little more. So we have a name for 1. Since we're starting with the third row of Pascal's triangle, we have a notation. And it looks weird. It looks like that. Couple of parentheses. On top, we have a 3, which is n. On the bottom, we have the 0, which is the number that we start counting at in the row. So what I'm saying here is this 1 right here is 3, 0. And we actually say 3, choose 0. Okay? And then this 3 right here is 3. The 3 comes from the n. Choose 1. And this 3 right here, we call it 3, choose 2. And this 1 right here, we call it 3, choose 3. I know that looks weird if it's the first time you've seen it, but you'll get used to it real quick. So this 3 right here is what I just called 3, 1, 3, choose 1. This 3 is the 3, choose 2 from row 3 of Pascal's triangle, which is really the 4th row. I know, it's weird. And then this 1 right here is 3, choose 3. So we say 3, choose 2. The terminology comes from probability theory or counting theory, depending on which way you look at it. But we're not going to go there yet, but that's what it's called. So this notation, n choose k, so n on top, k below it, parentheses around it. We say n choose k when you see that. And it stands for, it's just notation, it stands for the binomial coefficient of a plus b to the n from the term in the expansion whose variable part is a to the n minus k times b to the k. You'll see this a little better when we write out what's called the binomial theorem. But just keep that in mind for now. I'm going to come back to that, to where this comes from in a minute. So without using a calculator or a formula that you might have learned in another class, compute 4, choose 2. Well, I mean, we already did it, but let's do it again. What's the worst that we have to do? 5 total rows of Pascal's triangle, right? To get 4, choose 2, we also go in according to that 2 in that row number 4. However, we start counting at 0 again. So 4, choose 2, this guy right, just to make it hopefully perfectly clear, this guy right here, so in other words, n is 4 here in this row. This row, this value here is denoted as 4, choose 0. This 1 right here is denoted as 4, choose 0. So that this 4 right here is denoted as 4, choose 1. And this 6 right here then would be what? 4 choose 2. So it's equal to 6. Is that clear how you use Pascal's triangle to compute it? You just have to remember to start counting at 0 to get down to the right row and then in the right amount. Does that make sense? Okay. You can also do it on the calculator. I'll show you that in a little while. There's also a formula for it, which we won't get to. You're either going to use Pascal's triangle or your calculator to get 4 choose 2 or any other binomial coefficient. Let's use Pascal's triangle to get 3 choose 3. So which row am I going to focus on now?
Row 3.
Row 3, which is the 4th row down. It's the one with the first 3 going left to right after the 1. It's the one with the 3, right? That's how you can remember it. So you start counting at 0. So this guy's 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3 is 1. So this is a big theorem, the binomial theorem. The assumption here is n is a whole number, like 0, 1. Well, 0 is not very interesting. 1's not very interesting. So like 2, 3, 4, 5, 6, blah, blah, blah. The binomial theorem does work for non-whole numbers, but we don't present it at this level. You get it in Calc 2, perhaps. So the binomial theorem looks like this. Using that notation for the binomial coefficients, and an exponent of n, it turns out that a plus b to the n expands to be, well, the first binomial coefficient would be n choose 0, a to the n. And then the next term is going to be, well, if you write it in descending powers, the coefficient, of course, will be n choose 1. So this bottom number just goes up by 1 every time, and the top number stays at n. So that's easy enough to remember. And then the exponent on the a goes down by 1 in each term, right? If you write it in descending powers of n. A to the n minus 1. But then the exponent on the b, which starts at 0, so you don't see the b to the 0 here because that's just 1. The exponent on the b goes up by 1 every time. So it's n choose 1, a to the n minus 1, b to the 1. Okay, see if you see the pattern. What would the next one be? N choose 2, a to the n minus 2, b to the 2. Let's do one more. N choose 3, a to the n minus 3, b to the 3rd. Now, it keeps going. Let me shrink this. Make some room. It keeps going, and I'll finish it off in a second, but I want to point something out. The exponent on the b matches the number that you're subtracting off the n for the exponent on the a. Did you notice that in each step? Works here as well, works here, and whoops, pointed at the wrong thing. And here. And that's exactly where that generic term came from a little bit ago. If you look at, say, the kth term, where k is between 0 and n, then the kth term would be, okay, by the way, also this bottom number matches the exponent on the n, right? On the b, rather, sorry. This bottom number here matches the exponent on the b. So those are some observations that are going to come in very, very handy. Okay, so let's look at what the kth term should look like. It would be n choose k times, okay, what would the exponent on the a be? N minus k. N minus whatever this number is right here. And then b to the k. So that's the pattern. And then eventually, I'm going to put another dot, dot, dot in there. So I'll shrink this down even more. So that's the kth term, and that's where this guy comes from that I was talking about a minute ago. And then eventually, what's going to happen though? Plus dot, dot, dot. Eventually, the counter number beneath the n is going to get up to n itself, and choose n, which means the exponent on the a is 0, n minus n, so you don't write it down, and the exponent on the b would be the n. And that's the binomial theorem. In this example, you're asked to find the fourth term in the expansion of x plus 2y to the 12th. So you're asked to find the literally the fourth term. So we're not saying n is equal to 4 here, so you got to be careful about that. Well, okay, what would the binomial coefficient be on the fourth term? So generically, n choose k. Well, n is always going to be this exponent up here on the binomial that you're expanding. So that part's easy. But if you start counting at 0, what's the k going to be for the fourth term? Not 4, 3. So that can be tricky. But then you just use this formula to get the variable part of it, right? So now that you've figured out what the k is, it's 3, not 4, you can just fill in for the a and the b. And then a is equal to x and b is equal to 2y. We'll fix that in a minute. So it would be a to the, what would it be? What would the exponent on the a be? Well, let's do the b first. What would the exponent on the b be? No, the b. If we do the b first, the exponent's always on the b is always that. It's the thing we call k. The exponent on the b is always the thing we call k. Oh, and my notation kind of stinks a little here because I'm putting in more than I was originally gonna. So putting in the full formula would be a to the n minus k, b to the k is what we said, right? So the exponent then, that's generic. And then for this particular expansion, the exponent on the b then would be 3, like you said. And what would the exponent on the a be? 12. You just have to subtract these two. That's kind of nice notation to remind you of that, right? 12 on the top, 3 on the bottom. Oh, the exponent on the a is just going to be that subtraction problem. If you think of it, it's not really a subtraction problem, but that's how we can align it vertically if you want to think of it that way. So 9. 12 minus 3. But wait, there's more, because we think of a as x and 2y as b, so we got to fill that in. So fill that in, what do we get?
X to the 2y to the 12.
12 choose 3. I thought we said x to the 9th.
Oh, sorry.
X to the 9th, and then 2y. Now, the whole thing cubed, right? Would you guys buy that? Everybody okay with that? So what do you have to do when you're cubing the product 2 times y? You have to cube both the 2 and the y. So what does that give you? 8y cubed. Now, I don't really want to write down Pascal's triangle out to row 12, do you? I mean, you could. It wouldn't take that long. But I do want to show you how to do that on a calculator. On the calculator, the notation looks a little different. You're going to type in the 12 first, which makes sense. Go to the math menu, and then go over to PRB because this notation, what you're doing here, comes up a lot in probability. So PRB for probability. And you see the NCR? That's another notation that's used for n choose k, or the way your calculator denotes it is n choose r. So hit number 3 or go down to number 3 and hit enter. And then it was 12 choose 3, right? So you get 220. 220. So this 12 choose 3 is 220. But don't forget, we've got this 8 in here. And so you're going to have to take the 8 times the 220. What's 8 times 220?
1760.
1760 x to the 9th y cubed. Let's go ahead and do the full expansion of x minus 4y to the 5th. Let's make that triangle again to get the binomial coefficients. Okay, fill in the next line for me. What is it?
1, 1, 2, 1.
1, 2, 1. Fill in the next line for me.
1, 3, 3, 1.
The next one.
1, 4, 6, 4, 1.
The next one.
1, 5, 10, 10, 5.
Do I need another one?
No.
No, I know that this is the 5th row because the first number from left to right is a 5. So these are my binomial coefficients. No calculator needed. This is faster than using the calculator to figure out what those binomial coefficients are. In this case, because n is relatively small, n is 5. So let's write down the generic binomial expansion, a plus b to the 5th. What would a plus b to the 5th power be? Okay, you should know that the first coefficient is going to be 1 without even looking at this. So the first term is going to be a to the 5th. Plus, okay, use the next binomial coefficient from the triangle. 5 times, okay, what's a going to be to here? 4, it goes down by 1. And then b to the, b is going up. The exponent on the b is going up, the exponent on the a is going down. But, oh, here's a good way to remember it. The exponent on the a and the b have to add to be 5. Does that make sense? Yeah. Okay, so just 5a to the 4th b. Plus, what's the next binomial coefficient? 10, this guy. Okay, then it must be a to the 3rd b. Got to be 2 for 3 and 2 to add to 5. That's a good way to think about it, right? You can't go wrong there. What's the next one going to be? 10, right? This 10 right here. A squared, b cubed. The next one? 5ab to the 4th. The next one? It better be b to the 5th. By the way, earlier I mentioned descending powers. Well, I was referring to the descending powers of a. The powers of b are ascending, right? So, well, that's actually kind of fun, I think. But now it gets a little nasty. What's a in this case?
X.
A is x, looking at that guy right there. And what's b?
4y.
Ooh. You got to include the negative because the binomial theorem is for a plus b, right? So that means the terms are going to alternate. When the exponent on the b is even, you'll get a positive term. When the exponent on the b is odd, you'll get a negative term. And that's something to keep in mind because then if you put a negative in the wrong place, you'll notice. So what the a to the 5th is really just going to be x to the 5th. X is a. So let me make some room here. So x to the 5th plus, okay, 5. A is x, so that's easy, right? X to the 4th. And then b is negative 4y. That's easy enough. We'll calculate that in the next step. Plus, give me the next one. So you're filling in 10a cubed b squared with the appropriate a and b. 10 x cubed.
Negative 4y squared.
Yeah, and if you feel like it, since it's easy enough, you could go 64y squared. Oh, I'm sorry, 16, excuse me. Said it's easy, and then I messed it up. B squared would be positive 16y squared, right? So if you want to fill it in right away, if it's easy enough, go ahead. And then what would the next one be, this guy?
10x to the 4th.
10x squared, right? And then b is negative 4y cubed, which is going to be negative 64y cubed. And you could put that in right away if you wanted to. I'll do it in the next step, I guess. 5, the next one, 5 times x negative 4y to the fourth, make sure you put it in the negative 4y, make sure you put it in parentheses, because that means the negative 4 is brought, that factor of negative 4 is brought to the fourth as well, and the negative is going to go away for that term. And then the last one, negative 4y to the fifth, filling in this guy. Does everybody agree with that? Okay, let's calculate this. We get x to the fifth for the first term. What's the next one?
Minus
20 x to the fourth times y plus 160 x cubed y squared
minus 640 x squared y cubed.
Yeah, that's true, because this guy is negative 64 y cubed, right? So that will put that the minus sticks around because of the odd exponent, so that'll make it minus. Okay, 64 times 10 is the 640 that you mentioned, and then x squared y cubed. I think it's a little harder. What's 4 to the fourth? Is that 256? But it'd be positive, right? Negative 4 to the fourth will be 256. So okay, just to save a little bit of time. So this is 256 y to the fourth times 5, which is 1280. So plus 1280 what? X y to the fourth. Okay, and then what about negative 4y to the fifth? Will the negative stick around? You bet. And then what's 4 to the fifth? 1024. Don't forget the y to the fifth. Well, that was fun. I think you should stay home on Friday night and do those. No? Okay, that's okay. I didn't do it either. Believe it or not, I wasn't as nerdy back then when I was your age. So there you go. There's a full expansion. Instead of doing the next problem, it's kind of more of the same. Well, I will mention one thing. I'm going to let you go early since I've let you go late a couple times. Now, this one's a little bit different because it says find the term in the binomial expansion 3r plus 2s to the ninth that contains s to the seventh. So generically, which term are we looking for? So remembering the generic formula, n choose k, it goes a to the n minus k, b to the k. So in this case, what's the n? 9. And what's the k have to be? Since the 2s is acting like b, what's the k going to be? It's going to be the 7, right? Because the exponent, they're saying this is going to be the exponent on s to the 7th, which will be the exponent on 2s to the 7th. The factor of 2 won't make a difference. So it looks like this: 9 choose 7, and then the rest of it's determined for you. I won't fill it in, but so generically, a to the n minus k, that's just 2, right? And then b to the 7th, you fill it in, and that'll be the answer. And use the calculator to find 9 choose 7, because it'll be a big number. Okay, I'm going to let you go almost 4 minutes early. Wow, what are you going to do with all this extra time? Ask questions if you got them. Come on up. Otherwise, have a great weekend and finish your homework.
I'm going to cure cancer.
Well, that's a worthwhile endeavor.